This is part 2 of lithium versus lead-acid batteries. In part 2, we're going to cover equalization charge, parallel versus seriesing of batteries, and balancing lithium cells and various other things. If you have a 4-stage charger, then you have a charger with an equalization mode to it. The equalization mode cranks up the voltage about a volt more than the normal absorption stage of the charger. And this is done either automatically or manually. And if it's done automatically, it could be every day for, say, 15 minutes or every month for a couple hours. The why is it's trying to keep sulfur from sticking to the lead plates. It's trying to get that to dissolve and go back into the acid. And the pulse that it leaves on there, or the charge cycle, is usually around 16.1 volts, which is a point where the battery acid starts to percolate and bubble and convert to hydrogen and oxygen, which means after a equalization phase, you got to check your water levels and make sure they're up and not threatening to expose the top of the plates. You also need to be aware if at that voltage, not everything should be connected to the battery at that point. So like this inverter, it can go up to 16.5, so it would be okay, but your radio at 15.8 may complain about that voltage and cause some potential damage there. So you shouldn't have delicate components hooked up while it's going through the equalization charge. And also be aware you should never run an equalization charge on a lithium battery. It can completely destroy the battery. Equalization and stratification. The acid in a battery is denser when it's charged than when it's discharged. It becomes more water. So as it discharges, the watery acid floats to the top and the denser acid drops to the bottom, and it stratifies within the battery, and the battery doesn't work right. But the equalization causes the percolating bubbles that allow you to stir up the acid so the battery can work properly. Okay, parallel versus series as far as calculations go for voltage in amp hours. So let's say, for example, we've got this two parallel wired batteries, two 12-volt batteries. Each of them's 100 amp hours. So what's the amp hour rating of them combined? Well, it adds up to 200 amp hours at 12 volts. As opposed to the two series batteries that go out over in here, they're twice as many amp hours as those 12 volts. They're 200 amp hours each, but they're 6 volt. So if we wire them in series, we end up with a 12 volt battery, but it's got a 200 amp hour rating. It didn't double the amp hours, just the voltage. So we could parallel and series a battery bank at the same time. So take, for example, this 4 batteries here. There's 4 6-volt batteries, and 2 of them are in series down here on bottom, and the 2 on top are in series. Then we wired each of those pairs in parallel. So you end up with a 12 volt 450 amp hour bank if each of these is 225 amp hour 6-volt batteries. Now there's a reason I went with that odd sort of number, because that is the actual amp hour rating of that very common T105 golf cart battery. So if we took 4 of these golf cart batteries and wired them up like this, we'd end up with that sort of bank stat. So if your plan B for power is to take all the batteries out of the cars sitting on blocks in your front yard and then wire them up in parallel, or whatever cars are broke down in the neighborhood, then you can probably should count that out. Because what's going on here is if you wire all those together in parallel and you charge them up, say, the day before, they had resting voltages that were reflected like this: 12.7, 12.6, 12.6, 12.4. Then that 12.4 volt battery represents a battery that's only about 75% up to its capability after being charged. So you wire these all up with some cables, and what's going to go on here is the 3 good batteries back here are going to try to bring this bad guy up to speed, and it's just wore out, so it's never going to get there. You'll just drag these 3 guys down on the left here down to its level, and you'll end up wondering, why can't I get anything out? This whole bank would have been better without that battery at all. You could still use that for something potentially if you just got to put it on its own solar panel, its own charger, so it's not dragging down the other guys in parallel.
Even if all the batteries are brand new, this wiring configuration isn't going to work for us. That's because during peak periods of current, any amount of resistance in the daisy chain of wires going back to the battery in the back will result in voltage drop along the way, and that will cause the front battery to give a whole lot more capacity than the back battery. So much more that it's over discharged continually, and the battery starts going bad. And then the back batteries, which were good, will have to give up their capacity trying to bring up this bad battery, and it'll be unsuccessful in that, and you end up just wiping out the entire battery bank.
So if we decide to go with a 24 volt bank instead of a 12 volt bank, and we wanted to supply that same basic load, then we'd only draw half as much current. So the 50 amp that we're pulling out of all these batteries would cause a lot lower, half as much voltage drop across the battery, so we'd be able to get by without damaging batteries half as much just by converting to a 24 volt bank, which is one of the many advantages to going with a higher voltage along with smaller copper wire sizes and smaller charge controllers and things like that.
Another thing we can do is to remove one of the power leads from the battery on the right and rewire it to the last battery in the chain. This allows to pull current evenly from the front and the back battery. It will overutilize the batteries on the end if we still have some resistance in here, and underutilize the middle, but the problem will be half as much.
An even better configuration is to use bus bars across everything and then still pull a plus off towards one end and the negative off towards the other end, and that would mostly get rid of your problem altogether. An even better option is to just limit your parallel loads for batteries or to no more than 2 batteries deep on paralleling batteries, and try to go with a series configuration if possible. And just know that Bioenno, if you go with lithium batteries like this, even at 2 batteries, they recommend you do not do that with their batteries. If you need a larger battery, you just got to buy a larger battery. They only go up to 300 amp hours, so that kind of limits you in that regard. Battleborn, on the other hand, says it's okay to do that, but you need to buy the batteries from them at the same time. Let them know you're going to run it in parallel or series, and they'll make sure that the internal resistance of those batteries are matching, and so they'll draw current the same when you go back to charging them. Okay, so what's wrong with this setup here? You got 4 batteries with 2 series, and then those wired in parallel. Well, what's wrong is we should have taken the leads there on the negative and not connected there and brought it off this back battery. That way we've evenly drawing power off the back pair and the front pair, and we don't end up wearing out this front battery, the top batteries in this drawing, and underutilizing the batteries on bottom. If you're really going big with lead acid, then the way to go is with L16 batteries, where these are like 300-pound batteries, and they're just one big cell. Like a normal 12-volt battery has 6 cells in the one housing. This has just one cell in each housing, so you need 6 of these big 300-pound batteries wired in series to equal 12 volts, but that would cost you about $2,200 and weigh about 1,800 pounds. But it is theft resistant. Okay, when you store a lead acid battery, you really want to get that battery back to 100% state of charge, and you can apply a float voltage, and the float voltage is correctly applied. It won't hurt that battery at all. You do not want to put a solar panel on there and just let the solar panel be your float voltage, because the float voltage from the solar panel is going to be around 18, and that can cause your battery acid to percolate off, and you end up getting exposed plates and things like that. Lithium batteries, on the other hand, don't like to be at 100% state of charge. doesn't hurt them a lot like leaving a lead acid discharge will hurt it, but it will give you more charge cycles if you don't push it all the way to 100% all the time. So if you leave it at 50% is ideal if you're just going to long-term store the thing. And but if you need it in emergency, you need it to have some capacity at that point, then leaving it at 80 gives you still a lot of the advantages of not charging it all the way, but most of the capacity. And also, if you leave it at that, every few months you should fully charge it, and then you can, discharge it back to 50 if you want, or just leave it there and let it self-discharge, which is very minor self-discharge. But the question is, why do we have to fully charge this thing every few months? What's going on there? The reason we have to top the charge off once in a while on a lithium battery is because that's the point at which the built-in battery management system is designed to level the charge out across the cells within the battery. So for storing this battery or using this battery around the 8% state of charge, and if in use we're saying we're draining to say 50 or 40% or something and back to 80, and we're going up and down in that range, we're charging, discharging these individual cells, but we're applying it to the ends and charging them in series. But if one of these batteries has a little more resistance or less resistance than the other, then they're going to charge and discharge unevenly. So we can charge this thing up to what we think is 80%, but if it's uneven on the inside between the different cells, then it actually may be something like this, where 3 are 90% and one of them's at 50%. So as long as you're using that in a shallow depth, you may not even notice it. Probably wouldn't notice it. You wouldn't have any way of knowing that. But the problem comes when you go to pull a lot more than 20 or 30% out of it. So if we have a battery that was like that, then when we go to use 40% of the battery, that one low cell will drop to 10%, where most battery monitoring systems will then recognize it has a problem, and it will shut the output of its battery off. You don't think about that in lead acid, it can't shut itself off, but that circuit card in there is monitoring this for this situation just to be able to protect itself if one of its cells gets too low. So if we were to fully charge this up, then it would automatically level all the cells off, and then we wouldn't have to worry about, hitting one prematurely when we thought we had a lot more capacity left. Also, one of the disadvantages of lithium is we can't use it when it's below freezing outside, or we can't charge it. We can use it in that we can pull power out of it, but if we are not aware of it and we can charge that battery, if we try to charge that battery, we could damage a battery permanently. Now, some batteries, the better batteries you pay a little bit more for, like the Battleborn, it has an internal sensor in there for temperature. It will not let you charge that battery if it's below, I think it's a little bit less than freezing. So there is some self-protection there that goes along with the battery management system. So when we come to charging deep cycle batteries, you need to figure out what that charge current is and buy a charger rated at that current. It's not like a starter battery where you got a 8 amp charger or a 60 amp charger, and it's a lot more flexible with the charge current that a starter battery can use in your car. You can throw some high current at it and it can recover and you can start your car. But deep cycle batteries, that's one of the shortcomings of deep cycle batteries in lead, is it won't take a fast charge without potentially damaging it. So you don't want to buy too small a charger, because if you're having to run your generator in emergency to recharge your battery and you only have, say, a 10 amp charger where you needed a 20, now your charge time may have went from 6 hours to 10 hours. And you got to run your generator just to get your batteries back. So you don't want to waste generator time and you don't want to abuse your battery. So you buy the right charger. So you bought a lithium battery and you want to save some money by reusing your old charger. Now, if it's a trickle charger, there's a good chance it'll undercharge
your battery, which may or may not be that bad, but you have to monitor the voltage it's actually put in there and know whether that's it's matching up. Now, if you got some other charger, other nut besides a trickle charger, there's a good chance it'll overcharge your battery and force it into a over voltage shut off, or if it is a balanced battery that you've bought used, there's no protection in there, so you could damage your battery. Also, once you've charged up that lithium battery and it shuts itself off and everything seems to be working, then that charger is monitoring the voltage to know when it should turn back on, and the lithium battery voltage doesn't drop off like a lead acid, so the lithium will almost be dead before the charger kicks back in. Also, if you've got an equalization mode capability in your charger, then if you accidentally turned it on, that could also damage your new lithium battery. Also, if you've got a smart charger, whether it's made for lead or lithium, and your battery is run down into a mode that it shut itself off because you've over discharged it, and then it creates a problem for the charger we'll talk about next. So if you've got a lithium battery that shut itself off because it was over discharged, then the battery will have a way of bypassing that shut off to get a charge back into the battery. So you probably some diode or something bypasses a switch and allows you to send current in even though it can't detect any current out. And that diode you would have to hook up a current controlled power supply of some sort to it in order to give it a charge, but not too much charge that would exceed the rating of the battery, and bring it up enough to where then that switch closes, then you could hook your normal charger back up to it. So how do we measure the state of charge of a battery? With lead, it's pretty easy. The lead, voltage of that lead acid battery starts draining down and down and down, and it's somewhat linear as it discharges. So we just look at the voltage of the battery and we can tell what its state of charge is. So for example, in this chart, we have between 40 and 80% of the depth of charge is got over a volt split on a lead acid battery. But the same depth of charge range on a lithium battery has only 1/10 of a volt difference between it. So it's almost impossible tracking the state of charge on a lithium battery by the voltage. So how do we take care of that? So with a lead acid battery, you can have like a fuel gauge on the left here that is just basically a voltmeter that is displayed in some bands here that gives you a feel good about where you're at. Since on a lithium battery, it pretty much would just live in the green the entire time, and then right before it died, it would just sink real fast through the yellow into the red. So what the solutions that have come up with are much more complicated, unfortunately, in cost. Like this Victron, it's a kind of the cream of the crop of these type charger or battery monitoring systems, and it will measure through the shunt that's in the middle here the amperage going into the battery as a charge and the amperage coming out of the battery while it's loading. So it's keeping track current going in and out of the battery both directions all the time, and it adds or subtracts that to the overall capacity of the battery. So you have to set that up beforehand. You can basically charge it up all the way up and say this is the 100% point, and I've got a 100 amp hour battery, and then it will count off percent wise or tell me how many amp hours is left. The Victron, that $180, something else that gives you, it's got a Bluetooth connection to an app that you put on your phone, and you look at trends and things like that that are all interesting if you're sitting around in your RV with nothing better to do. Now, what I've stumbled across is this AILI battery monitoring. It's a fraction of the price. It's under 40. If you buy it through AliExpress, you can get it for almost half that price. And there's a 50, 100, and a 350 amp range available in this particular configuration. So this is much less capable. There's no Bluetooth, but it does tell you the voltage, the amps, the amp hours coming in or out, and the percentage of the battery that's left, and a little indicator on the left here, left of the 8,
tells you whether it's draining or charging, and then it flashes kind of a slow uh, gradient flash off and on as it charges to let you know it's in that mode. But if you just want to know how much is left in this battery, then this is a fairly economical way to go. Okay, we said earlier that the liquid inside a charged battery, the spheric acid, is denser or heavier than what it becomes, which is mostly water, as it discharges. So the way to tell the state of charge, one way of doing that is through a hydrometer. And they use hydrometers in batteries and in wine and other things, but you basically use this uh, device on the right here, and we just suck up some fluid out of the flooded lead acid battery into this, and we see how much this little float in here floats within that liquid, and wherever the top of the uh, liquid cuts across, then that'll tell us if it's charged or not. And you should check every cell individually after you've charged it up, and there should be no more of a deviation of 500ths between cells, and that if there's like one cell that's way low, that tells you that cell is shorted out on the inside or something, and the battery's bad. Okay, the question comes up, can I charge the battery and use it at the same time? Well, let's say you've got a solar system, or it could just be a normal charger over here on the left, and it's capable of supplying 30 amps of charge into this, lithium battery here. It could be lead, it could be anything, it doesn't matter. And I've got a load over here of 20 amps. Now it can supply 30, and I've got a load pulling 20, so what happens here is if I'm in a charge cycle at this point, the load will show a little lower resistance than the battery, and the current will flow from the charger straight to the load and still charge the battery at about 10 amps. Now if I draw a little more, say 30 amps, then basically I'm just going to pull all the charge current into my load, and there'll be no current flowing in this branch going to the battery. Now if I bump that to a 40 amp charge, I'm still going to draw 30 from that charger, but it'll all go to the load, and I'll pull an additional 10 amps out of the battery. Okay, well that's it. Hope you enjoyed this and learned something. If you don't remember me saying anything about equalization charge, that means you fell asleep about, halfway through. So that'll gauge that on how far to scroll back and hit play again. If you're looking for something to deal with solar electric small, medium size designs, then a similar type presentation I've also done that I'll upload on that as well. So have a good day.